Okay, everybody, as we move into 7-6, we've been talking a lot about exponents and the rules about exponents and how to deal with exponents, but today you're going to recognize exponential functions, and you're going to learn a lot about their graphs and a lot about their equations. The definition of an exponential function is the function of the form y equals a times b to the x. Notice the exponent. A can't be 0 because that entire equation would be 0. And b's got to be bigger than 1, okay? B shouldn't be positive 1 though. X has to be a real number. So let me first of all define what this means up here, okay? You cannot have y equals 0 times 2 to the x. Why can't you have that? Because 0 times anything is 0. So that's not technically an exponential function because a can't be 0, okay? So that is not an exponential function. Something else that's not an exponential function would be like if you have 4 times 1 to the x, because it doesn't matter what power you take 1 to, whether you do 1 to the 5th, 1 to the 6th, 1 to the 800th, it's just going to be 1. So this will never be a changing equation. That is not an exponential function. That's kind of what this sentence is trying to say. The last thing you need to understand is not an exponential function is, let's say you have y equals 3 times the quantity, negative 2 to the x. That is not an exponential function because your equation would go negative, positive, negative, positive, negative, positive, because no matter what this x was, if that x was odd, it would be negative. If it was even, it would be positive. That's not an exponential function because it wouldn't make a real pretty line for us. Okay? Now let me make sure you do understand this. If you had y equals 3 times negative 2 to the x, that's a lot different, isn't it? You see that negative sign? It's just not where it belongs. That would be y equals negative 3 times 2 to the x. The negative would come out front. So that one is an exponential function. This one is the same function. Maybe I should draw an arrow like that. This one is not because the negative would have the exponent. Again, it would go from being negative to positive, and it really wouldn't be a function. That's not what a function is. All right. First thing you're going to do is, and these are the pictures, by the way, of the different types of exponential functions. Notice this one opens up, this one opens down. These are two different kinds, two different ones, okay? This one opens up, see how it kind of like points to the left. And this one opens down. I'm going to teach you the differences between these 4 types of graphs. All right? You see this one that opens up like this? That would be if you have y to a positive number to the x power. It would open down if you have like you would have a negative sign, but then you would have a number to an exponent. So that's what that looks like. All these numbers, notice the 2 is bigger than 1. So like 1.5 would look like that, 1.6, 1.7, 2, 3, 4, 5, 6, 7. Now look at these ones over here. You see how these ones like go the other directions? Like these ones grow. These ones technically shrink. And that's because this time we have fractions being raised to a power. We'll talk a lot about what it means to be exponential growth versus exponential decay in the future. Now how do you identify, okay, let's separate this. How can you identify if a table or an equation is linear exponential? Now remember, linear is a straight line, and exponential is like a graph like the one above. It looks like a J kind of. That was a really bad example, but it looks like a J if it were to take a turn and stuff. Well, here's what you're going to look at. Do the y's increase by a factor? In other words, would you multiply to get to the next one? If that's the case, it would be exponential. And then you kind of consider your y's and you say, do the y's increase by a constant? That means you would add to get to the next one. That means that this would be linear. Okay? This equation, exponential, is what you just learned, y equals a times b to the x. Sometimes more often than not, a is 1. And linear you learned with Mr. Linkus. Y equals mx plus b. All right. Let's look at our two options in problem 1. Now, obviously in part A, you're given a table, right? Tables are the easiest thing to try to determine what it is. Notice, please, that the x is increased by 1. If the x is increased by 1, here's how we do our check. How do you get from one to the other? I hope you notice that to get from one to the other, you multiply each time by 3. I hope you agree. Well, since it has what we call a factor, right? Just like I said in part A, you have to multiply it. That's called a factor. The factor of 3, because they're like going up times 3 times 3, that's going to be exponential. And now we can actually make an equation. I'd like to teach it to you, okay? It's y equals, we do our factor to the x power. Now, I am going to tell you it's a negative, because you see these numbers here, they're negative. We'll talk a lot more about this in a little bit, okay? Let's look at part B. Now this time, I gave you an equation. An equation is sometimes more difficult, but sometimes it's easier. Because you see how x isn't an exponent? That means this has to be linear. It actually takes the form, I hope you agree, it takes the form of y equals mx plus b. B just so happens to be 0 in this problem. Let's say, well, that you didn't quite sell me, Mrs. Angeli. How else could I tell? You make yourself a little table of values. Okay? Plug in 0, 1, 2, and 3 for x. And then you can kind of like prove that this is actually going to be linear. It's going to be like a y equals mx plus b. If you plug in 0, you get 3 times 0 is 0. If you plug in 1, you get 3 times 1 is 3. If you plug in 2, 3 times 2 is 6. And if you plug in 3, 3 times 3 is 9. Now what's happening each time? We are multiplying by 3, are we? This time we're simply adding by 3 to get to the next one. This proves, just like I said up here, that it increases by a constant because you have to add to get to the next y. And they already have the equation, but it would be y equals 3x. Okay, so this one's linear, and this one's exponential. Moving on. Take a look at your tables. Notice that x increases by 1 on the top. So what we need to do is take a look at the different, how it increases. I hope you notice that on each one you need to add 2. I was hoping kind of if I took a break there you would think to yourself that you need to add 2. See how it's add 2? Add 2 means that that's a constant, which means this particular equation would be linear. Now we're not going to make a y equals mx plus b because they don't give us the 0 point, and they don't give us the 0 point. You can make a y equals mx plus b, but you have to do like, you have to find the slope, and then you have to do y minus y1 equals m times x minus x1. So it doesn't ask us for the equation, so we're not going to make it. That was just a little extra we did on the front. Now look at part B. Part B is real easy, guys. They actually give you the equation, so let's just look at it. Do you see that x is an exponent? Well, if x is an exponent, guys, that must mean that this is an exponential equation. End of story. You don't even need to do a table because x is an exponent. It has to be exponential. And it is really just that easy. Okay? Problem 2. Population growth. This is kind of neat. Well, except that it's about bugs, and that's kind of gross. But otherwise, it's really neat. Suppose that you have 30 flower beetles, and they are left undisturbed in a warehouse bin. The beetle population, yeah, this is kind of gross. The beetle population doubles every week. The function f of x equals 30 times 2 to the x power gives the population after x amount of weeks. How many beetles will there be after 56 days? Okay, before we go on, I do just want to explain, do you see this 30? This 30 is always your initial amount. This 2 comes from the fact that it doubled. And that's how they came up with their equation. So you can do that equation on your own. If they tell you how much something starts with and what's going on, if it starts at 30 and it's doubling, you can make that equation. Also in this problem, I really want you to notice that they talked that it doubles each week. Did you notice that? But then they gave us this in days. So we need to notice that we need to convert our days into weeks. And we can do that, okay? We have 56 days they want us to plug in, but we're not going to plug in 56 days because if we plug in 56, that would be like how many weeks, because that's what the equation says. I hope you know all you have to do is divide by 7, right? And 56 divided by 7 makes 8 weeks. So 8 is actually what we're going to be plugging in. So here we go. My function, do that cursive little f, after 8 weeks is defined by my original amount of 30 times 2 to the 8th power. Remember, this doesn't mean f times 8. This is actually just saying my function defined at the value of 8 is, so that would be 30 times, well, 2 to the 8th power, I have my answer key here, it's 256. And then you work it out one more time and you get 7,680, and that is how many beetles there will be after 56 days, or what we defined as 8 weeks. That wasn't too bad, especially when they give you the equation. The next one, okay, we got rabbits. Rabbits this time. The initial population of 20 rabbits triples every half year. That's going to be very important for us. That's my phone going off. Every half year, it triples. The function f of x equals 20 times 3 to the x power, 20 because that's the initial, 3 because it's tripling, gives the population after x half year periods. Okay, so what they're saying is time is measured in half years. How many rabbits will there be in 3 years? So they're giving us 3 years, but that's measured in half years. So you need to think about it like this. Can you please convert 3 years, because that's what they're giving us. Can you convert 3 years into blank half years? You guys can do this, right? How many half years fit into 3 years? Well, half and a half makes 1. Another half and another half makes 2. Another half and another half makes 3. So that's 6 half years. 6 is the number we need to be plugging in because that's what our equation says you need to be plugging in, half years. So we're going to do 20 times 3 to the 6th power. I'm going to put my little defining thing on here. My function base defined at 6. So you can type it in actually all at once. 20 times 3 to the 6th power. And that is how many rabbits there will be after 6 half years, or 3 total years. So there will be 14,580 rabbits after 3 years. 3 years makes more sense, so I'm going to put that on there rather than write 6 half years, because we know what 3 years is. Okay? Moving on. This time we really